Hello everyone! Today we'll be talking about quantum algorithms. A quantum algorithm is a series of unitary operations, measurements, and classical communication in the right order designed to solve a problem. Today we'll see how specific properties of the function f of x can be revealed using these algorithms. We'll discuss quantum algorithms that use the function evaluation depicted here, where the upper qubit bundle correspond to the argument register and the lower qubit bundle to the function register, where the value for the evaluated function will be stored using bitwise addition modulo 2. We will also encounter situations where a Hadamard is applied on every ket in a register. And when they're all in ket 0 and there's L of them, an equal superposition of all possible number states of the L qubit bundle is created as shown here. If L equals 2, then the ket 00 state gets transformed to this. Notice that all the double-digit binary numbers are represented. Here's the generic quantum algorithm we will focus on today. It starts with the qubits in the argument and function registers being in ket 0. The argument register qubits get to be made into a superposition state using the multiple tensored Hadamards, while the qubits in the function register get prepared for the next step by the gate U sub A. After that, gate U sub F evaluates f of x for every value of x in the superposition in one single step. That's quantum parallelism for you, the beating heart that gives quantum computers their power. After that, the argument register qubits are operated on by U sub B, in preparation for the measurement that will reveal what we want to know about f of x, which we finally perform. Before we delve into today's first algorithm, let's consider the simplest possible constant and balanced function, where the function f of x and its argument x can only take two possible values, 0 or 1. When f of 0 equals f of 1, we say f of x is constant. Otherwise, it's balanced, meaning the cases with values 0 and 1 are equal in number. Classically, to reveal whether it's one or the other, we have to evaluate f of x twice for x equals 0 and x equals 1. Because, for example, let's say we're told f of 0 equals 0, we cannot deduce anything about the nature of f of x without knowing what f of 1 is. Is there really no way to figure this out with only one evaluation? Well, Deutsch's algorithm has the answer. This is the quantum circuit that represents it. Note that there's only one qubit in each of the argument and function registers. The total state starts in ket 00, and as it progresses in the quantum circuit, it evolves into other states. At this point here, just before measurement, the total state will depend on whether f of x is constant or balanced. If it's constant, the state will be this. And if it's balanced, it will be this. Notice the difference between them? In the first case, the argument register is in state ket 0, and in the second case, in ket 1. So all we have to do is measure it, and if the measurement result is 0, this tells us that f of x is constant, and if it's 1, this means f of x is balanced. That's with only one single measurement. We couldn't do that in the classical case. Now, let's look at an extension of this algorithm, the Deutsch-Jozsa algorithm, where we're still assuming that f of x is either constant or balanced. The difference here is that instead of there being only one qubit in the argument register, there are L of them, and consequently, the single Hadamard on the register is replaced with a tensor product of Hadamards. Again, just before measurement, the total state is given by this if f of x is constant, and by this if it's balanced. Upon measurement, if x equals 0, i.e. all the qubits in the bundle are in ket 0, then f of x is constant, and if it isn't, f of x is balanced. The final algorithm we will discuss involves searching through many objects to find that single one we're seeking. Let's look at this example of a bag with 3 toys inside, 2 blue and 1 pink. We want to take the pink one out, but we're not allowed to look while we're doing that, so we can succeed after 1 try, 2 tries, or 3 tries. If we get it from the first try, we're very lucky. But if it's after 3 tries, then we have the worst luck. On average, we get the pink toy after 2 trials. If we have 2 to the L teddy bears in total, one of which is pink, then on average, after 2 to the L minus 1 trials, we find the pink bear. This is the classical situation. Now, instead of bears, we have the function f of x, and instead of pink and blue, we have 1 and 0 as possible values of f of x. Only when x equals a, f of x equals 1. Otherwise, it equals 0. If x can take 2 to the L values, this means that classically to find x equals a, we have to make 2 to the L minus 1 searches. So the question is whether or not quantum power can help us do better. This is the quantum circuit for Grover's search algorithm. Again, it conforms to the generic quantum algorithm we're focusing on, except that it repeats the gray part of the circuit with U sub f and U sub b gates m times. Together, these two gates act as a rotation. The state before measurement, ket phi m, depends on m. If P of A is the probability of obtaining outcome A upon measurement, then each time the gray area is implemented, it increases a little bit. And as m increases, it approaches 1. This is achieved when m is in the order of the square root of 2 to the L. Compare that to the classical 2 to the L minus 1 situation. To get a feel for it, if L equals 100, this advantage can be achieved in only 2 to the 50 trials quantumly, but on average 2 to the 99 classically. The difference becomes even more drastic when L is even bigger. Before I leave, I have this question for you. In the algorithms we discussed today, where are the qubits entangled? إلى اللقاء.